sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. I wonder how long it took him to sign autographs. Fortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the molar. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea of how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so how big is a mole? I'll say the number. It's enormous, right? It is literally the biggest number I can't even imagine. The Earth 5 miles deep in donuts, the basketball size or basketballs that make up a planet, it's a humongous number. So like I said, nobody's got time to count those. But we are going to be converting between the number, the mass, and the volume using concepts that they kind of just talked about. So these are our 3 new big ideas that are going to allow us to talk our matter into quantities that we're more familiar with. We can take matter in terms of atoms and convert it to mass, something that we call molar mass. So we're going to kind of start to talk about using everything we've learned thus far, where we've taken the subatomic particles, we've built atoms. Then we took those atoms, then we made compounds. We made ionic compounds, we made covalent compounds, we made metallic compounds. So now we actually are not very, very familiar with the types of compounds that are out there. We're going to start to convert them in terms of their quantities of them. And this is going to get us into some of the more math-based part of chemistry. And this initial part is called compositional stoichiometry, so it's production composition of the compounds that we've been talking about. Stoichiometry is just chemistry math. That's it. It's dimensional analysis. You remember that, your old friend from Unit 1? Dimensional analysis where you wrote the division and your multipliers on top and bottom. You canceled units. You're like, yes, it's back. All right. So these are the three big ideas. And I'm going to show you it on another picture in just a second because I want you to see it, how it kind of looks like a train station. So I'll come right back to this. Here's my picture. The mole can be related to number of particles, the molar mass of something, and the molar volume of something. So the mole is the stepping stone that's going to be allowing you to convert from any of those three bubbles on the right side to any of the other three bubbles. The three bubbles you see here. So every single conversion is directly related to the mole. And we're going to talk about how each of them are related. So atoms, what's FU? Formula units, thank you. And molecules. These are referring to different types of particles that are based on the type of bond that's present within the compound. So atoms are just atoms, right? If I said an atom of iron, that's referring to an element. Just a normal old element off the PCOE. If I say a formula unit, what kind of bond am I referring to that's present within that compound? Ionic, good. So you saw that in your book some. This is more of an ionic compound term that we'll be using. So you'll only say formula unit for anything that's ionically bound, metal and nonmetal. And molecules, you guessed, would be referring to covalently bound things, right? That's usually referring to a covalent compound. Okay, so the factor that's comparing moles to particles is this is how we count things by particles, formula units, molecules. What number is the comparison between these or the conversion between these? Avogadro's number, right. So the conversion between moles and any number of particles is Avogadro's number, which is 6.022 times 10 to the 23rd particles per mole. Per 1 mole, if you want to get real technical here, it's per 1 mole. 6.022 times 10 to the 23rd particles per mole. So that number is going to allow you to either convert from particles to moles or from moles to particles. You can do it either way. You just have to flip the fraction if needed. We'll do a lot of examples today with that. All right, so that's concept number 1, particles. Well, instead of counting things out, sometimes we prefer to literally mass them on a scale. So the conversion between mole and molar mass is going to be the mass of the compound we're talking about. It's very different for every single compound out there in the world. Okay, so this is a standard number, Avogadro's number. This one is going to be different for every single compound. So let's look at, guess I got periodic tables out. You're going to need periodic tables today. I want you guys to tell me the mass of aluminum oxide. So aluminum oxide, you got to think about the formula first. I want you to tell me the mass of it based on what you think you should be doing with the molar mass. How do you achieve the molar mass? Melanie, what is aluminum oxide? Beautiful. Aluminum oxide, Al2O3. All right, you're going to want to calculate now, okay? How much does 1 aluminum atom weigh? 26.98, right? Okay, we have 2. So put in your calculator, 2 times 26.98. That's just the aluminum component, right? So this is how you will calculate molar mass for every single compound. Like I said, it's different because it's dependent on the dang formula. So in your calculator, we just put 2 times 2, 26.98 grams. Plus, how many oxygens do we have? 3 of them, and each oxygen weighs what? 16.00, right? So we'll do 3 times 16.00. What's the molar mass? Oh my gosh. Oh wow. What is it when I what? 101.96 grams per 1 mole of aluminum oxide. So aluminum oxide weighs, in this case, 101.96 grams per 1 mole of it. It's always per 1 mole. So this is a conversion factor, or a CF as we previously denoted. This can be flipped if we need to, depending on if we're starting with converting from moles to mass or from mass to moles. So we'll use that. But this is only for aluminum oxide. It's going to be a different number for water, for carbon dioxide, for phosphorus pentachloride. Like, we could keep going, but you just have to know you're using the masses from the periodic table and adding them up. Okay, so that's how we convert between those two types. So that's the relationship between mole and mass. The last relationship is with a gas at room temp. At STP, which we call molar volume. So this is only at STP that we can use this conversion. And look on your reading guide. What was the number that was told to you that should have been associated with molar volume at STP? Thank you, Melanie. So 22.4 what? Say again? Liters per, can you guess? 1 mole, right. So the conversion between moles and volume of a gas at STP is 22.4 liters per 1 mole of that gas. So everything is per 1 mole. But which number is it, has a variety of numbers that go along with it? Which conversion has a variety? Molar mass, right? The standard numbers that you should know are molar volume, 22.4 liters per mole, and the particles, which is Avogadro's number, 6.022 times 10 to the 23rd. Okay, so what I want you to notice, I know it's kind of jumbled up over there. Are there any direct conversions between particles and molar mass? Is this connected? Is it directly connected? No. How do you have to get from here to here? Go back to the mole. Right, so if I give you particles and I say, okay guys, I got 8 particles of oxygen, 8 atoms of oxygen. What's its mass? You're like, well, I don't know. You have to go from particles back to mole, which is like the train station. Get off here, get on your train, go back to molar mass. There is no direct conversion between these, nor is there between these, or anything on this side. Everything's going to have to go back to mole, and then to your final destination. Okay, nobody's going to get hurt on the final destination. Okay, so this is that, all that right there. I just basically explained that first slide that we had here. Okay, so those are our 3 conversions. So this is on your sheet. This sheet I see you do. So the first part, here. We kind of already got this. We know it's an SI unit. That's on your reading guide. You know the conversion. So the definition of the mole will allow us to convert between moles and particles. This part is not actually on there, but thumbs up if you understand that. Mole allows to convert from moles to particles. And then there were 3 representative particles, and I already wrote them down for you. But if you need a little bit more information, this is basically what we just wrote, but in kind of a bubble map form. The 3 representative particles refer to different types of compounds or matter that we're dealing with. If you're saying atom, you specifically are referring to something straight off the periodic table, an element. If you say the word molecule, you'll be referring to something that is covalently bound. And if you say the word formula unit, you're referring to something ionically bound. And so I have some examples here. Sodium chloride is our example for formula units. Iron is composed of iron atoms. And then what's the formula for water? H2O. Give me one of those diatomic molecules that we talked about, gosh, like a week ago. Say again? O2 is one of them. Give me another. F2. Ooh, I'm gonna go in order. Do you remember the big 7 in hydrogen? So H2, here, I'm going to just do this right here. H2 is over here. And then what's the big 7 in hydrogen? What's the first one of the big 7? Nitrogen. Okay, next. Oxygen, and then chlorine. Okay, and then down. Chlorine, bromine, iodine. Okay, so it's the big 7 hydrogen. Those are all the diatomics on the periodic table. Can I go forward? Some of this, I like the bubble map because it gives you everything at once with some of the details that are actually very important. Okay, this picture is supposed to show you stuff that you already know about outer shapes and stuff. So look at this first guy here. Looking at the single spheres. What type of particle is that of the three? Is it an atom, a formula unit, or a molecule? Peyton. Atom, right. This is an atom of neon. These are multiple atoms of neon here because they're single units. They're not a bond. They're simple elements. Looking at this one, what would you say it is? Everybody? Molecule? Why? Why? Because it's a diatomic molecule, meaning a diatomic covalently bound compound. Look at this one. Woo, doggies. Big guy here. What is that? That is ionically bound, right? So what's the term we use to describe that? Formula unit, right. And then this one? Formula unit. And these are actually what they look like. You can see this is, do you guys know the name of this? Ammonium dichromate. Good. Ammonium dichromate. Name of this one? Cr2O3. Say again, chromium what? Chromium what? 3 oxide. Good, because that 3 is describing chromium's charge. And then we've got what kind of particle over here? Molecule. And then another molecule, because this is water. Okay. So you can actually see descriptions, and I can have you describe a chemical reaction in terms of the terminology that is representing each of the particles. Okay, cool. So, skipping this, oh no, do I have this in your paper? I have this in your paper, so go down here for me. We have sulfur, right? The mass of 1 mole of sulfur. Can you guys see your periodic table with the lights off? 1 mole of sulfur. What's its mass? 32.0 what? 7 grams. Good. You just simply looked on the PTOE. These numbers are not coming out of our tails. We are actually finding these numbers, and everybody should see sulfur weighs 32.07. Okay, so slightly different phrased question. How many atoms are in 55.8 grams of iron? Say again?
1.
No. What are you saying? One what? Are you saying 1 atom? You're saying 1 mole. Okay, so what's the significance of 55.8? That's the atomic mass of iron, right? So the atomic mass of iron, 55.8, is equal to 1 mole of iron. But how many atoms of iron is that? There you go. You see, you actually just converted in your head. That was an easy one because I gave you the exact mass of iron, which is equal to 1 mole of iron. But the question was not what is the number of moles. It's what are the number of atoms. That's equal to 6.022 times 10 to the 23rd atoms. You actually did 2 conversions just in your head because you know their equivalencies. But we're going to actually write out our work on some of these other ones. Okay, another slightly differently phrased question. If I wanted 6.022 times 10 to the 23rd atoms of carbon, that's what I want. What mass of carbon would I need? Everybody? Everybody's saying 12.01. Where are you getting that number from? PTOE. So you said, so this means I want 1 mole of 1 mole of carbon. So if I want 1 mole of carbon, you look on the periodic table and you say 1 mole of carbon is equal to 12.01 grams of carbon because that's what its atomic mass is in the periodic table. So those are the 3 relationships we're working on. Okay, let's do one more thing with molar mass. Let's pick our arch enemy here. This one. This one's a little different. You see the 2 on the outside? Ooh, what's the name of that? Magnesium what? Nitrate. Be strong and confident. Okay. So magnesium nitrate weighs what? Tell me the pieces of it. Use your words. So an atom of magnesium weighs what? 24.31. Okay. Keep going. Good. Okay, so now we're realizing we have a parentheses around this happy family called nitrate. We have 2 nitrates. Well, that means we actually have 2 nitrogens and how many oxygens? 6. Okay, so there's 2. This is magnesium. There are 2 nitrogens and there are 6 oxygens. All right, so what's nitrogen weigh? 14.01 grams. And each of the oxygens weigh 16.00 grams. So math. Again, 1. Thank you so much for helping here. Okay, 148.33. Thumbs up. You got that? Okay, you guys should be actively engaged with the calculator so you don't make silly mistakes later on. That's the molar mass of magnesium nitrate, and that's molar mass per mole of magnesium nitrate. Do you feel comfortable finding molar mass? Give me a thumbs up if you feel comfortable finding molar mass. The ones with the polyatomics are the only ones, like specifically with the parentheses involved, that you need to make sure you distribute. But other than that, it's pretty straightforward. Okay, I'm feeling good. Ooh, what's the name of this guy? Do not say di or anything, because it's an organic one. Ethane, good. What's the name of this one? Now this is not organic. Dinitrogen pentoxide, good. Okay, this one, I don't have to prove to you the molar mass now, I think we got it. Do we need to write anything down here? The STP definition, you have it on your reading guide? So you know that it's 1 atmosphere for standard pressure. And what is this in Celsius? 0 degrees Celsius. That's supposed to be on the other side. 0 degrees Celsius. Good. And do you remember how to convert from Celsius to Kelvin? You just add 273, right? So if I have a Celsius temperature, you add 273 to get to Kelvin. But we actually will, I will always just say add STP. Right now we're assuming STP. Later on in life, we will not assume STP. We'll do more math. Okay? So here we go. Let's actually start getting to the conversions, which I think, here we go. This is, on your paper, class examples. All right, everybody have a calculator? So I want to show you the processes my chemistry teacher taught me. And we kind of already approached it with our dimensional analysis way back. Always identify your known, meaning your given, and your unknown, because that's your question. These questions are set up without, they're not big word problems. They're very straightforward to get you started with, okay? So on number 1, what are we looking for? What's our unit of interest? Mole, right? So our question is mole. Silicon, right? Moles of silicon. What's our starting point? Like the only other thing up there in low. Okay, great guys, thank you. So that's our starting point, that's our given. 2.80 times 10 to the 24th. Please write down these examples with me because you have to do the rest of them after I do the class ones with you. Atoms of silicon. So you have your big bubble map in front of you. We have to convert from atoms to moles. Is there a direct conversion between those? Everybody, yes or no? Yes. What number is associated between them? Okay, Avogadro's number. So when I'm writing down Avogadro's number and I'm writing mole, which one goes on top? Mole, 1 mole. The number 1 is always going to be with mole most of the time if it's in your conversion, factor. 1 mole of silicon has how many particles in it? There you go. 6.022 times 10 to the 23rd. And what's the particle name here? Atoms. Atoms, right? Okay. So there are 3 terms for particle. It's either atom, formula units, or molecule. You can say particles, but that's kind of cheap. You want to be more specific. So we have the conversion practically done, guys. We just got to start calculating. You're going to make sure you put parentheses around anything with an exponent like that. So 2.80 times 10 to the 24th. I'm going to do this with you. So I'm not going too fast. And you're going to make sure that when you multiply, so just in case you forgot, you're multiplying across by 1 because 1's in the numerator, which don't worry about multiplying by 1, nothing happens. But then you're going to divide by 6.022 times 10 to the 23rd in parentheses, or your calculator will not know what to do with that exponent. Give me a thumbs up when you got it. Maddie, what'd you get? Okay, I'm going to stop here. Times 10 to the what? Oh, times 10 to the nothing. Times 10 to the 0. Sorry, I was looking at my bullet that said 10. So, how many sig figs do you think we need? 3. Good, because this is our number here in the front, 3 sig figs. This is not a measurement. So, not a measurement. If it's not a measurement, that 1 mole is kind of like a placeholder. So it's a comparison. Do not record to 1 sig fig. Record to 3 sig figs. So, what do I need around to? Right, so this would be 4.65 moles of silicon. You guys know where silicon's used in the real world? Huh?
Masks.
Okay. Mass. Why would you need a silicon mask? I was going to say solar cells. Okay, great, guys. I've showed you this before, haven't I? This one makes this. That's a solar cell. This is a silicon disk. It's also in computers, microchips. It's very conductive. This is one crystal. Lots of silicon connected, but it's one crystal. So anyway, they're used in solar cells too. Okay, now let's go to the next step. We have moles, and we are wanting grams, right? So question, grams of what? And what's the symbol for potassium? K. And this is our starting point, 0.32 moles of potassium. First question in your mind, is there a direct conversion between moles and grams? Yes, what is it? What's it called? What's the big term is molar mass, right? So what's the molar mass of potassium? Thank you. Everybody should look at me, look down at the periodic table, look back, and it says what? Say again. 39.1 grams. And I'm actually accidentally already told you that number goes on top. This is the number of grams that's equal to 1 mole of potassium. And why am I putting moles of potassium on bottom? Right, and I didn't show you up there, but I will. So moles of potassium cancel, getting me to grams of potassium, which is what my original question was. So is this done? It's a single stepper, right? So multiply. It's going to be about a third of that, 0.32 times 39.10. Total mass? 12.512. I'll go there for now, but then you gotta tell me sig figs. 2 sig figs, right. This is my limiter over here, 2 sig figs. So 13, good, you're rounding up to 13. So 13 grams of potassium. Very good. Those both were single steps. Next one, tell me, do we have 1, 2, 3 million steps? What do you guys think? Think this through. Okay, what are we starting with? Start with moles of what? That's not an ion, that's just a whole molecule. Negative prefixes. Sulfur trioxide. So we have a mole or some number of moles of sulfur trioxide. It's not asking for sulfur trioxide at the end, it's actually asking for oxygen. So we're going to have to dissect this molecule of sulfur trioxide to see how many atoms of oxygen are in it. Well, let's just say I had 1 molecule of sulfur trioxide. Draw its loose dot structure. What sulfur trioxide looks like? And your sulfur in the middle. I know you've already counted. There are 24 electrons, right? Totally. Okay. What's it look like? There's just 3 branches. You guys are super not talking to me right now. With options on them, great. Reading your mind. Okay, so dots and everything. Double bond. Fantastic. Okay, that's what it looks like. If this is considered 1 molecule, so 1 molecule of SO3, how many atoms of O are in here? How many atoms of O? 3. 1, 2, 3. We can see them. So I've just made this my own personal conversion factor. 1 molecule of SO3 has 3 atoms of oxygen in it. That is now a conversion factor. Doesn't that make sense? Right? So my goal in thinking through this first is to go, okay, if I've got moles I've got to start with, what's the next thing I want to convert to so I can implement this? I want to use Avogadro's number to convert to molecules of sulfur trioxide. And then my last step will implement this because then I can actually use it and get to atoms of oxygen and then have party. Okay, so starting off with 1.14 moles of sulfur trioxide. Sometimes it's nice to think it through before you start because then you might go on the wrong train. And then you go back to the train station and then you miss your other train, so you know. Okay, so what goes on the bottom? 1 mole, right, 1 mole of sulfur trioxide. What goes on top? You just told me, Matt. And we're talking about converting to what? Molecules, right? Molecules. So moles and molecules are not the same thing. Moles are like a big number, molecules are a thing. Okay, molecules of SO3. Okay, so then that's going to allow for the moles of SO3 to be canceled. I'm not done yet. I'm just showing my work as I go. And then, what do you guys think is going to be the next one? What goes on bottom, I mean? I actually want atoms of O on top, right? So I want to get 2 atoms of O, so I want goes on top. So I will put that up top. 3 atoms of oxygen. And then what goes on bottom? Yeah, just 1 molecule. Because now that I've gotten 2 molecules of SO3, I can then just go say, okay, I'm going to consider one of them and count how many atoms of O are in there. And that's what we do on the board. 1 molecule of SO3. So that allows for a molecule of SO3 to cancel from here and here, leaving us with the question that I didn't write, atoms of O. Okay, so calculate, calculate, calculate. And convert to sig figs when you get there. Avery, you got me? Yeah. So how many sig figs do we need there before? Yeah, so 2.06, or because it says 5.9, right, or 5.8. So we round up to 6 times what? Beautiful. Atoms of oxygen. There you go. 2.06 times 10 to the 24th atoms of oxygen. Who's feeling good so far? That was our first 2-stepper. Okay, let's keep it on then. Moles to grams. So question, grams of what is, ooh, this is where nomenclature is going to come and bite you in the butt. If you don't know it. Ready? What's the formula? I hear P-O what? Uh-huh. There's a 3 here, right? Okay, because it's crisscrossing down. Sodium phosphate. I will not give you formulas. I'm going to say names as best I can on most of these things, okay? What am I starting with? Good. 4.52 times 10 to the negative 3 moles of sodium phosphate. Okay. Is there a direct conversion between moles and grams? Yes or no? Yeah. Yes, it's called molar mass, right? Let's find the molar mass of sodium phosphate. I'm not going to write it out. I'm going to ask for you to put it in your calculator. Okay, so ready? What's sodium's mass? 22.99. How many sodiums do we have there? In the formula, 3. So you're going to 3 times 22.99 plus, or you might just be 23 on yours, it depends. Plus what? What's phosphorus weigh? 30.97 plus how many oxygens? 4, so 4 times 16. You might accidentally remember some of these, which would be really nice. So you're going to see oxygen quite a bit. You'll accidentally remember it's 16 like all the time. Okay, so what goes on bottom? Right, your mole, because your mole on top needs to go on bottom because it needs to be canceled out. 1 mole of sodium phosphate. And its mass? Good, 163.94. And this one you don't have to round because it's not our final answer. So keep your mass as big as you need to there. So that's sodium phosphate. Okay, that times your first number and divide by 1, which you don't need to. What we got? Point what? So how many sig figs? How many sig figs? 3, good, because this front number up here, 1, 2, 3, those are 3 sig figs, so 0.7 what? 41 grams of sodium phosphate. Good. Okay, let's do this last one together so that I can make sure we, the last conversion we've not touched yet. Oh, I'll do both these. We'll do this real fast. Okay. Actually, you guys try these. Try these too. That will help you in just a second, but I want to see that you can get started. You know, once you get started, you're right there. Half the job just showing up, guys. right, what did you guys do for your next step after you were done your given? Okay, I'm hearing 1 mole, I'm hearing 22.4 liters. Why are we not able to just go to atoms? There's no direct conversion there, so we can't go there. So you're going to your best friend, the mole, and you're putting 1 mole of CO2 on top, and you know that we're talking about liters at STP. It doesn't say it STP, but I said to assume it. And that's going to allow for us to cancel out our liters of CO2 here and here. So now we are at this great place, moles of carbon dioxide. Not moles of oxygen, but moles of carbon dioxide. So what do you guys want to do next? And I don't know that the mass will be helpful. It might take us kind of on the wrong track, and we'll come back, but we can always get there. Just what's the shortest route? So we use that question number. What are we converting to, though? There are no such thing as atoms of CO2. That's the wrong word, right? Molecules. We will be converting to molecules of CO2 because molecules represents a covalent compound and CO2 is a covalent compound. So it looks like a linear structure, right? So 1 mole of CO2 contains 6.022 times 10 to the 23rd molecules of CO2. Okay, now we're getting down. We had a big mole of them. Now I can pick out 1 molecule. What does 1 molecule look like? It's got a carbon in the middle and what? 2 oxygens on it, right? So you know how I created my own conversion? I like doing this because if not, we'd have to go to like 3 more steps. This is the simplest route, okay? So think of CO2. What would our conversion be for that? So 1 what of CO2? 1 molecule of CO2 has 2 atoms of oxygen in it. You guys okay with that? The understanding what a molecule and an atom is? It's real, that's what it comes down to. So if you want to say that, then that's what we're going to use this. Now, since we have molecules on top on the last one, we have to put 1 molecule on bottom here. 1 molecule of CO2 contains how many atoms of oxygen again? 2. And you can see the subscript there. You don't necessarily have to draw it, but I'm just trying to bring in your old stuff that you still remember. 2 atoms of oxygen are in 1 molecule of CO2, and that gets us to our desired heat. So, moles of CO2 cancel, molecules of CO2 cancel, atoms of oxygen win. So, you guys calculate across. Don't forget to divide by things that are on the denominator. Give everybody a chance for a second. Scott, what'd you get? What you got? I'm just trusting you, right? Try it. Who else got this? 1.3, and then atoms of oxygen. Okay. Last one. With me. Formula units to grams. Is there a direct conversion between formula units and grams? No. We already know we're going to have to touch what? The mole. And don't be offended. I do just put a few. And then you guys tell me the formula for that. Van? Who agrees? PBI 2? All in favor? Great. So, lead 2 iodide. And I can't do much with formula units. That's like a number of things. Matt, what do you think we should do? Not you. Yeah. Well, formula units. What does that remind you of? Particles, right? If you think particles, what number comes to mind? Avogadro's number. Okay, so we're going to have to use that someplace here. Scott, pick up. What do I do with it? Why am I putting it on bottom? Right, so formula units need to be taken care of, right? We're going to take it out, but formula units must go on bottom on the next fraction. And since formula units are representing a particle, the number that goes with particles is Avogadro's number. Right, so this is going to go on bottom. 6.022 times 10 to the 23rd. And what is that related to? What is that equal to? 1 mole of lead 2 iodide. So this is where we mount the mole. Paige, what would you do next? Because our formula units have been taken care of, right? So that's our particles are now converted to moles. Now we want to convert moles to what? Right. Is there a direct conversion between moles and grams? Yeah. What's it called? 2 words. Yeah. Molar mass, right? So, whip out that calculator. What's the molar mass? Lead 2 iodide. what am I typing in my calculator? 207.20, so 207.2 is lead's mass. You're finding lead on TTO, you see it. And, ooh, iodine, 126.9. Awesome. There's two of them, though, so break 12 by 2. And what's your total mass of lead? 2 iodide. 461. And does that mass come top or bottom? Everybody? Everybody says top because you were converting to that, so it has to go on top. If not, your groups will not remain on top. To lead 2 iodide. So 461 grams of lead 2 iodide is equal to 1 mole of itself. 1 mole of lead 2 iodide. So that last conversion allows for us to cancel moles of lead 2 iodide on bottom and on top and bottom, leaving us in grams of lead 2 iodide, which was our question here. And you calculate by doing 1.91 times 10 to the 21st. And then this is where you have to implement parentheses. So what I usually do is I'll just put the first number times 1 over parentheses, or just divide, since it's 1 here, you just divide by what's in parentheses here. And then at the end, we'll multiply by 461. Hey, where'd you go? 2.7. I gotta make sure this is right.
Oh, sorry, that's most.
Oh, give me the whole shebang. What's the final column?
The final one?
Yeah.
That was 2.7.
I got 1.46.
That's what I
That's
meant.
all.
Okay. There's some mammoths.
No, I put in the bottom times.
Got you. Okay, so yeah, 1.4636 all the way. Yep, 1.46 grams of lead 2 iodide. Okay. So who feels a little bit better about the 3 relationships? Okay. Yeah. Question? You're raising your hand. Okay. I want you guys to look below. There are 8 questions. I'm about 8 questions. Let's do with that. We're gonna have them all done by tomorrow. I want you guys to do a couple of them for about 15 minutes. Then I'm going to try to do bowls of chocolate with you outside. Okay? So work hard for 15 and see where we are. Please write either on the back of this paper or on a separate sheet of paper. And I write next to that little teeny box so I won't be able to see them very well. Okay? And I like to be able to make sure I see your units, all the decimals, you know. Straight your stuff here, people. I'm getting ready to come look at them right now. I'm making my way. Sorry. I'll leave these here for you.